Hi. In chapter 2, we're going to dive into linear equations. Linear equations are going to be a focus of 8th grade and 9th grade math because they're so common in real life examples. And it is coming off of that last section in chapter 1, which was literal equations. So most linear equations are a form of a literal equation. You have an x and a y, and typically the x is called the independent variable, the input, and y is called the output. We'll talk about that a little bit more when we do functions, but here's an example of a linear equation, y equals x plus 1. Now, why is it called linear? Well, for the very simple fact that when we graph it, and I'll talk about that in a minute, we get a line. But what are we graphing? That's really what students have difficulty understanding. Literal equations have two variables. And so since x can be, if I choose anything for x, I'll get a different y. So it's a case where there are infinite possibilities. There are an infinite set of numbers that will make this equation true. And since there are two variables, x and y, when we talk about a solution to a linear equation, we have to mention two numbers. So this equation has an infinite number of solutions, infinite solutions. So I can't just say, tell me the solution. I might ask for a solution, a single pair. And that's the other piece. The solutions are pairs of numbers. Solutions are pairs of numbers. So when we ask you to graph it, we're asking you to show us in a picture what all the possible combinations of x and y that will make this true. Well, we can't we can't make a table with every single pair of numbers, but we can make a table that has a few pairs. So here in this column X, they meaning whoever wrote the book, chose to choose input values of -1, 0, 2. I want to emphasize they could have chosen anything. They happened to choose those numbers. Then using those input values for X, they follow the equation, add 1. So -1 plus 1 is 0. 0 plus 1 is 1. 2 plus 1 is 3. Once they have their input-output pair, they wrote it as coordinates, x and y. This is one possible solution to this equation because this makes this true. If I plug in this for x and this for y, I get an equation that is true. And that's all a solution ever is. So then they plotted those 3 points, and lo and behold, they lie in a straight line. And if we look along the line, we realize that every point on the line makes the equation true. For example, this point makes the equation true. That has the coordinates 1, 2. 1 plus 1 equals 2. But I didn't have to just choose a nice number like 1. I could have chosen -1/2. -1/2 plus 1 is 1/2. So the point -1/2, 1/2 is also a solution. So the main thing to understand as we start this exploration into linear equation is that we have infinite solutions to any linear equation. And when we draw a picture, the graph, we should see a straight line, and each point on the line represents a possible solution to the problem. So as we start this chapter, we just want to make sure we're capable of graphing these equations. And you're going to have many tools, and we'll use them in class, but I want you to have the background. So here's the first method we're going to use is make a table. So here's our example. Y, the output, is equal to -2 times the input x plus 1. So when you make your table, this is a full big table. We might take shortcuts later on, but this is the idea of it. You have an x column, choose some inputs. My advice is always choose small numbers and numbers that are easy to work with. That could depend on the graph itself. Now, also, on the equation itself. Also, taking a look at the graph. This graph is small, not in the sense of size, but it only goes from -3 to 3 and -4, -4 to 4, -4 to 4. With that in mind, I can't choose like 5 as my input. I'm going to get too big of an output. So looking at the graph, looking at the equation helps us make our decision. So now I'll follow the steps. This says multiply by -2 and then add 1. Multiply by -2 and add 1. Notice what I'm doing. I'm setting up the calculations. So I just replaced x each time. Now I do PEMDAS. 2 plus 1 is 3. 0 plus 1 is 1. -2 plus 1 is -1. So this column I set up there for your calculations. Some of you will be able to do that column in your head, but I would be careful. You're doing a lot of steps at once. Maybe it's best to slow down, at least at the beginning. So after the calculation, I can fill in the final column, which are my solutions. Are these the only solutions? No, they just happen to be the solutions that I chose to find. Now I'll plot them: -1, 3, 0, 1, and 1, -1. And they all seem to lie in a line. That's the key. So when I do this, if I see that one of the points does not make a straight line, then either I did a calculation wrong or the equation isn't linear. Eventually, you're going to be able to just look at an equation and know it's linear. And then you'll know to go back and check your work. Now I'm going to try to sketch this in. If we were doing this in class, we would have rulers. So I'm just going to try again. Let's use black. I'm going to have to see if there's an online tool for this. Better. And not the best. Anyway, so every point on this line makes it true, and that's why I have to draw the arrows in. The arrows indicate that this goes on forever and ever, because I could choose larger values of x, extend this graph this way, and I would meet the line down below. Now, it wouldn't be math if there wasn't some catch to it, right? So we see that this line is slanted down to the right. We'll talk about what causes that, and it's got a medium steepness, I would say. But you could definitely picture other lines slanted at different angles. We're going to look at the two extreme cases next. What is a line that's perfectly flat? What does that equation look like? A horizontal line. And what about a line that's very, very steep? Exactly vertical, right? They're going to be those extreme cases, and we want to see what their equations look like. So the first one is the horizontal line, when y is equal to a number. Okay, what kind of, that's going to cross a horizontal line. Let's see why. So as I look at this equation, it says y equals. Where's the x? That's my first thought. Is this just like an answer to our chapter 1 problems? Output equals 2? Not exactly. This is saying the output's 2, and we don't care about the input. Okay. How do I know that? Well, only because they gave me a coordinate grid to show the solutions. So the output's always 2. What is the input? Well, the input could be anything. So I could use those same 3 values. Input anything, output's 2. So I go to my table, I take my table and graph it: -1, 2, 0, 2, 1, 2. And that's how we get the horizontal line. This is the case where the output is always the same. And there's a surprising lot of real life situations where that's true. As we get into word problems, you'll see that. The output's always 2. Now, the vertical line is a little trickier. Okay. This is saying the input is always -1. Well, that's weird. We usually get to pick the input, right? And again, how do I know that this isn't a solution from a problem from chapter 1? The only way to know is from the context. And in this case, they gave us a coordinate grid. So they're saying this is a linear equation, draw the solutions. And it's saying the input is always -1. So this time I can't choose the input. I have to choose -1. But the output is mentioned. So I can choose anything for the output. So let's see what those points look like. -1, 0. -1, 1. -1, 2. And there's my vertical line. Input is always -1. So if I look at any point along this line, the x value is always -1. So this equation is a good description of that line. Likewise up here, if I look at any point along this line, the y value is 2. So this line is a good visual of that equation.